Log on, tune in, find out. Another good idea from Cambridge.
Session this afternoon. Our first speaker is Catharina Stroppel, who will speak on convolution algebras and explicit construction.
Thanks very much. Thanks very much for the invitation here. What I would like to present here is a construction of a convolution algebra. So many of the things which will turn up there won't be completely new to you. Some is very similar to old construction, which are very known. So I want to start with explaining you a little bit what convolution means in different contexts, and then do this explicit construction. And then tell you also where our convolution algebra turns up. So convolution algebras. So let me start first very basic, namely convincing you that matrix multiplication can be viewed as a convolution procedure. So let's say m times n denotes m times n matrices. Let's say over C, over the complex numbers. It doesn't matter really what we take there. And then we have, of course, the multiplication, which would take a matrix of size m times n and a matrix of size n times k to a matrix of size m times k, of course. So and we can view this as a convolution algebra by saying, okay, let's take m a finite set. So this m has nothing to do with this m, just a finite set. And we denote by Cm the functions from m to complex numbers. Then, of course, we can identify matrices of size d1 times d2 with functions on a finite set m1, m2, cross m2, where mi has di elements. And this is nothing difficult. And then this matrix multiplication just becomes convolution in terms of functions on this set. So then multiplication becomes convolution. Which means if I take a function on m1 cross m2 and a function on m2 cross m3, I get a function on m1 cross m3 just by convolving. So an f star g is by definition on m1, m3 just the sum of f of m1, m2 and phi of m2, m3. And I sum over all elements m2 in m2. So this is very easy. And this is the basic example of a convolution structure. So let me do another one, which is more related to what I want to do later on. Namely, we can do convolution product structure on de Rham cohomology. So what I want to do is very similar to the thing above, just from the setup. It's different, so I take m1, m3, 2, m3 now compact oriented manifolds. And I look at omega of mi, differential forms on mi. And then I can build a convolution product on these differential forms. m1 cross m2. By just taking a form here, how do I denote it? f12 take a form here, F23, and convolve it, which means by definition I would take the form F12, F23, and I pull it back to the triple product. So this Pij would be the projection from the triple product to Mi times Mj. So I will pull both of these guys back to this triple product, and then I integrate afterwards over M2. So and one can easily check that this is compatible with the differential. And therefore it induces a product on cohomology. On cohomology. So that's the second version of convolution. And now let's do the third one, which is another construction of convolution product on cohomologies, namely, so I want only to catch this, on Borel-Moore homology. So somehow the first example doesn't give really interesting algebras, I would say, except if you say matrix algebras are interesting, I don't know. So this is more interesting, but the last one here, which I want to give as an introductory example, is for instance used by Chris and Ginsburg to construct the affine Hecke algebra by using this convolution construction, which I explain in a second, on Steinberg varieties. So let me recall this, how this works. So again, M1, M2, M3, C infinity manifolds. I think, yeah, it's the same assumptions as over there. So oriented and compact. So and I want to do the easy version of this. So I choose a subset of M1 times M2, and I choose a subset of M2 times M3. So they should be closed. And then I do this construction, which I did here for the sets. So I define a convolution of the sets just by saying this is, so it's a subset in M1 times M3, given by all tuples, where I can find the M2 in between, so such that I end out in this element set 2, 3. So this is the definition of this product of these two sets. And I want to put a convolution product on a Borel-Moore homology. So let me write it like this, Borel-Moore homology to space. So in a specific example where I want to take Z to be the same thing, and M also to be M1, M2, M3. So I take the special example where all these M's are the same, and I want to define a convolution product on this subset S, on the Borel-Moore homology of this subset S. So, and this works exactly like here. So I think I don't have to write it down. If I take a glass in here and a glass in here, then I would pull it back to the triple product and push it forward again to Z. So exactly in a similar procedure as here. So this defines a convolution product. And for instance, if you would take the Steinberg variety for this construction here, so M would be T star of G mod B, and so I should say what Z is. Z should be a fiber product of M with M over N, where I have a proper map from M to some other variety N. Then this can be, for instance, taken to be T star of G mod B, the flag variety, here, and then over the nilpotent part. And then this would give the affine Hecke algebra. So an example of this Frisch and Ginzburg's construction of affine Hecke algebra. So what I want to say is this, at least there are interesting examples coming from such a convolution product. But what I also want to mention is that there is, I would call it a problem with the grading. If we put in the grading, we take something in degree I and j here, then we get something in degree I plus j minus the dimension of M2 in here. So it's not compatible with the grading, and the same thing happens here as well. So not remark. Product is not compatible with the grading. So, and all this background information was for me a motivation to construct convolution algebras using Springer fibers. So somehow do a little bit like this, but not exactly, to construct something like degenerate affine Hecke algebras, or to construct, hopefully, algebras which carry a grading. So what I have to change a little bit is I have to find a convolution product which is compatible with grading, and I want to have it explicitly constructed. So for this, I start now with the explicit part. So an explicit construction of a convolution algebra. So the setup here is I want to look at Springer fibers, so that means I look at first nilpotent endomorphisms of Cn, so nilpotent map. And then I look at the Springer fiber, which I want to denote by flag supper n. So these are fixed points of the flag variety. I take the full flag variety in C to the n. And I want to have it fixed under this n. Okay? So this is an interesting space to consider. So for instance, if we take n equals to 0, then of course if we have no condition over there, we would get just the usual flag variety. If we would take n to be the other extreme, so one Jordan block like this, then the Springer fiber is just a point. But somehow both of these examples are misleading, because in most of the examples of this n, we get, maybe I should write this here in general, FLN is not smooth. And this is a good thing for us, because we want to use irreducible components to get somehow a top degree of a cohomology, like in this part 3 over there. So we want to have many irreducible components to get a more interesting cohomology. So for understanding this, I want to recall an old theorem of Spaltenstein and Vargas. So which says the following. So let me from now stick to a particular case, because this explicit construction and even the construction so far only works in a very baby case. Namely, I want to assume we have only two Jordan blocks of our A. So this is maybe a bit too easy for you, but already in this example, it's not so easy to write down this convolution algebra afterwards. So I want to stick to this case. So let's say we have size n minus k and k. And let's say n minus k is bigger than k. So let me assume this. And then let me go back to the theorem. So the theorem says then that irreducible components in this string of fiber are indexed by standard tableaus of shape n minus k, k. So this theorem holds in general. It's not only in this case, but what is nice here, that I have another bijection, namely what I want to call crossingless matchings of n points with k cups. So I think the best thing, instead of writing down too many formulas, I want to tell you how this works in an example and only write the formula how to go from here to here. So here's an example. So let me do n equals to 4 and k equals to 2. That's the first interesting example in the case that not everything is smooth. So in this case, I have two standard tableaus. And I want to do the standard tableaus maybe in a different way as you are used to. It's neither French nor English. It's German maybe. So there are two of them. So I want to do them such that the lowest one is in the right down corner and it goes up like this and like this. So and I want to associate to this first a crossingless matching of 4 points. So I have my 4 points. And the matching is, I look at the numbers which are downstairs, this one, and I just connect them to the right with the other ones. And here one is the same thing. They are going down, so I would connect them like this. Okay? So and now I have to construct from this picture irreducible component. So I just do this by the following construction. So if I have a cup like this, then my space in my flag corresponding to the endpoint is just given by the space corresponding to the beginning, the starting point minus 1, and I take a pre-image of it. So where this pre-image is just built such that the dimension fits. So if you want to have a formula, you can say it's this thing here. So let's do this in this example. This example, what I first do, I would write down these spaces corresponding to the lower row, like this. So this would be 1, 3 and 1, 2. And then in this case, here, the second guy would depend on the zeros one by taking the pre-image of 0. And note this is a two-dimensional space because we have two Jordan blocks. So that means the pre-image of 0 is two-dimensional. And inside here, I would take 4 here, take the starting point, subtract 1, so it would be n to the minus 1 of f2, which is of course the same thing as n to the minus 2 of 0, which is my C4. Okay? And here downstairs I would get n to the minus 1 of f1, which is three-dimensional. And then here I would go along the big cup And a big cut means I have to take the second pre-image of that 0, which is again my C4. Okay? So in this, this is a particular case of these two Jordan blocks that I can write down these flags, a subset of flags, which gives me my irreducible components without having to take the closure of it. So normally what Spartenstein and Vargas did, they would go from here to here by giving you a locally closed subset, and then you have to take the closure. But in this easy case, everything is already given in such a nice form. So in particular, these irreducible components can be completely read off these diagrams. Yeah? So, let me introduce the notation that I take, say, a crossing-less matching A. I want to denote by the same thing as a standard tableau A, and then I have the corresponding component C of A. And one thing is missing, which I should mention. If I have an orphan point, which could happen if I have more boxes upstairs and downstairs, then my f of I is just some pre-image of the image of n. So these numbers can be read off of this diagram. I don't want to mention it, but what I want to say is that these guys are fixed, completely fixed spaces. So the only choice of spaces I have are the ones, the numbers downstairs. And what you can see here is, what is this space? I have a one-dimensional space in a fixed two-dimensional, and again, if I would factor this out, a one-dimensional and two-dimensional, so what this is just P1 times P1. And this is, again, an iterated P1 bundle, but it's not trivial. So this is an iterated P1. So now I want to construct a convolution algebra by defining the underlying vector space to be just the pairwise intersections of these components. So this is my algebra. What I wanted to put in here was also the name Fang, who made this specific connection here in this two-block type. So, and here's the first theorem. So this is all joint work with Ben Webster. And the first statement of the theorem says that the components, or even the pairwise intersections of the components, are iterated P1 bundles. And another thing which I should also emphasize here, that I really want to sum over pairs of components. So I distinguish intersection A with B from B with A, which might look a bit strange, but I want to think of these guys as idempotents in an algebra. So I want to multiply them from the left and from the right, and it should not be the same thing. So that's part A. And part B, I want to introduce a convolution product of these things by just taking a pairwise intersection and taking another pairwise intersection. Then inside there I have the triple intersection, and then I can go to the pairwise intersection like this. So this diagram defines me a convolution product on this H star by saying if I multiply something from A intersected B with C intersected D, then it's 0 except when B and C match. So I mean, I can restrict to such a case then. And then if they match, I take a class here, and I do exactly what was done in this convolution construction. I would pull them back to here, cup them, and push them forward to here. So this defines a convolution structure on H star. And in fact, this gives an algebra. So this gives an associative algebra. And there's a little slight complication with, or if we choose the orientations correctly. So what turns out, if we just would take the orientation of this manifold, which just is given to us by this complex structure, then this construction here won't give an associative algebra. I found this quite amazing. So it will give an associative algebra up to signs. So over Z mod 2Z, it's okay. But it's, in general, it's not okay. But there is a choice which makes it compatible. So I will say a little bit more about this choice a bit later. But what I want to do first, give you an explicit idea how this algebra looks like. So in particular, what we should start with to understand these cohomologies of these pairwise intersections. So and my idea here is to say, okay, to understand this cup product, or this convolution product, and also to describe these intersections, we want to see this everything embedded into our big space, which is the full flag writing. So let me state this as a theorem. So then, with Ben Webster. So I want to start with the cohomology ring of the full flag writing. And of course, this is not my theorem or our theorem. Yeah. So this is the well-known theorem of Borel, which says that the cohomology of the full flag writing is just the co-invariant algebra. So that means polynomial ring in x1 up to xn modulo invariance under the symmetric group. And I take the ideal of polynomials with all constant terms, which are invariant under Sn. So and now I have, of course, my Springer fiber, or the component of this Springer fiber, sitting inside there. So I would get a map going down here. And I can go one step further. I can take the pairwise intersection. So now I want to construct or describe these guys explicitly in terms of this co-invariant algebra. And the result is very easy. First of all, it's quite easy to see that this is surjective, and this comes from this part A here, that it's an iterated P1 bundle, so it will be generated by the images of the xi's. And what we get is that this is explicitly given as follows. So I take the x1 up to xn, and I have relations. Whenever I have a cup like this, I have the relation that the corresponding first term classes add up to 0. And if I have an orphan point like this, then it's just killed, so it doesn't give anything. And the last, so this is, if I have I sigma, if I have a cup like this here is if I have an orphan point, and the last one holds for every I. So this gives my explicit description, or if you want, you can say this is isomorphic to tensor product like this, where I runs through all left points of cups. So this somehow fits with the description over there, type A, part A, that I have here a cohomology ring of P1, and I have an iterated P1 bundle, and I take the tensor product. So this is very strange, I thought, because you don't see any difference between this case and this case in the cohomology. So you would see it if you would work over the integers, but you don't see it over the complex numbers. So they just are tensor product of the corresponding cohomologies of the P1s. And everything, again, is completely described by these easy diagrams here. So I would just take the endpoints of the cups, and then all the relations are depending from this picture. And here, we get the same thing. So I start with this description. I get again a tensor product of cohomologies of P1, where I run over all i's, which are the left endpoints of the components, which are closed, so closed components in A and B. So by this I mean the following. So if I would, for instance, take for A this thing, and for B this one, then I have to take here the left endpoint, and then they would label these guys. And whenever I have a relation, so for instance the x2 has a relation in the component A, so this would be x2 plus x1 would be 0, or the x4 has a relation in B with x1, and you check, because these are only, so you have to check that it doesn't depend on which way you go, but you always change only the sign. And because from one way to the other, the number of arcs I use is the same modulo 2, it wouldn't depend on which way I go. So that means what I can write here is, so xi is minus 1 to the number of arcs, which I use to go from j to I if I and j in the same component, in the same closed component. So I have a relation like this, and then I could also have a picture like I have a line going like this, for instance, some cups here. So this would be an orphaned line here, a propagating line. Which means I go from one side to the other. So then if I have a propagating line, I would put xk equals to 0. So if k is proc, k on a propagating line. So these are all relations, but sometimes this could be 0, this intersection, and it's 0 if and only if I have a line which is not propagating. So CA intersected CB is empty if there is a no non-propagating line. So that means a line which would start at one side and end at the other side. And if you are known to if you know temporally Lie algebras, this is exactly the non-degenerate invariant form on this temporally Lie algebra, and you have exactly this relation coming up there as well. So this I should write here if CA intersected CB is non-empty. So if it's non-empty, then I can write it again as a tensor product of cohomologies of P1, where I index these P1s by the left points of my closed components. So I just remove all the lines, and I take the left points of the remaining circles. Okay? So that means what this gives me is the underlying vector space of this convolution algebra. And there is an explicit construction of the multiplication. So which I just want to show you in an example. So there's a topological description of the multiplication. So, and people who know what Hovanov homology is will recognize this, because this is exactly Hovanov's construction of his algebra. But I want to tell you again what it is, and then also can say how this problem with the orientation comes in if I would choose the usual orientation on my irreducible components. So what we do is we want to multiply something like I take a component A, and I take the component B, I take the pairwise intersection, I take the cohomology, and I want to multiply it with the pairwise intersection of the cohomology B and C, and I won't end up in the intersection A, C. So I want to do one example. So let's say A is this, and B is that. So B would be again this, and C is this thing here, like this. So I want to construct something which goes from here over to there. Oops, sorry, I did the wrong thing. I want to go from here to this one here. This one here. So I try the same thing, A on the bottom and C on the top. And you get from there to there, but just putting this middle part into straight lines, like this. That's clear. So let's do this just step by step. So we start with two circles. So we would have twice the cohomology ring of P1. I just write Cx mod x squared, but of course we have it explicitly written as the quotient of this thing, so we know what the x's are as in terms of the xi's. So this one corresponds to this, and the other one corresponds to that. So then let's make this straight. Then we make one circle out of it, so that means we have only one left, and of course this is just the multiplication corresponding to this topological picture of a pair of pens. Then we do the next step. Make these two straight. So we go from, whoops, this shouldn't be correct. This is one circle again. Ah, it's two, good, yes, thanks. So it should be two, and it is two. So that means we go back to here. Here we take just the co-multiplication, which tends 1 to x tensor 1 plus 1 tensor x, and then we do the last step. And we have this one circle. So we do the multiplication. And this is going back. And this procedure defines, or this describes the convolution product. So in particular, what I should remark, this is Hovanov's algebra, which he used to define these knot invariants. And on the other side, it's also known by a result of mine that this Hovanov algebra describes subalgebra of the algebra describing perverse sheaves on a Quatermanian or parabolic category O corresponding to this parabolic given by our nilpotent element, the principal block of this. So in particular, this thing should have a grading, and what actually works out, that I should put part D, that this is a graded algebra. If we put some appropriate shifts on here, depending on A and B, and explicitly given again by these diagrams. So let me just quickly tell you what happens. So what I told you here is what happens if we choose these orientations correctly. And we don't understand really why we have to choose the orientation, how we do this. What we know is that this algebra, which I will say in a second, turns up as an X algebra of coherent sheaves, and also, which was our motivation to explain this explicitly, as a Floer homology algebra of an algebra defined by Seidel and Smith. So what we are computing is a Floer homology algebra, and then these orientations there turn up exactly, or this mismatch of orientations turn up there in sort of obstruction bundles of these Lagrangians. So this has some explanation which we don't understand yet, but what we understand is what happens if we choose the normal orientation. What happens is we can have two pair of pens in this picture, namely this one, or, I mean, of course, also the other one around. So this would be another one. But it could also happen that we actually get a pair of pens where the circles would lie one inside the other. And if we take the normal orientation, then we would get a minus sign depending on this nestedness of circles. So in other words, you can say the normal associative version you describe just by a TKFT construction like this, where you don't embed, and this strange non-associative version you describe via an embedded TKFT, where you include signs depending on how your circles are nested. This is somehow the difference. And one is associative, the other one is not. So, but let me at the end connect this to two other things. But before I do this, I want to make two other remarks. Namely, what is nice of this algebra, it is a symmetric algebra. But what is not so nice, I think, that it has infinite global dimension, because it's symmetric, the properties. So H star is symmetric. That's easy to prove. And it has infinite global dimension, and it's a cellular algebra in the sense of Graham and Lehrer. So everything can be described combinatorially. But what we want is, for instance, a quasi-hereditary algebra. So what we can do, so can extend this algebra to a quasi-hereditary one. So let me just briefly say this, how this works. So, so our components were indexed by standard tableaus. If you want to extend it, we can, for instance, go to semi-standard tableaus. And we have the corresponding cup diagrams, which now have the difference that they are not having k-cups, but maybe more, less than k-cups. And what happens is that they correspond to fixed points of a torus, namely the normal torus of GLN, of GLN, which acts on the flag variety, restricts to a torus action of a two-dimensional torus, namely just the part which commutes with our nilpotent element. So if I would look at the fixed points of this two-dimensional torus, then I can get a bijection to semi-standard tableaus. So and then we can associate to this fixed point P the stable manifolds. Or say attracting sets. So by which I mean I take my fixed point P, then I choose a co-character of my torus. So let's say I take this one, like this. So I have here my spring of fiber. I would have my fixed points, and I can look at attracting sets. So that means everything which is attracted to a fixed point when I let go t to infinity. So these are all x, such that if I act with t on x, then I get p for t goes to infinity. So and if I take a closure of this is what I call xp, and is an attracting set. And what turns out is, if I do this bijection here correctly, then the standard tableaus, which are a subset in here, will just give me the irreducible components. But the rest of these semi-standard tableaus give me something new. So for instance, if you take the example of P1, so n equals to 2 and k equals to 1, then I would get my component, closure of the component would be the whole thing, and the extra thing, which I have by an extra semi-standard tableau, would just be a point. So what I add is just a point. This is not much. But then I can do the same construction. So I take pairwise intersection of these attracting sets, that P and Q runs through fixed points. Again, ordered tuples. And then the statement is that this algebra is quasi-hereditary. So it's the quasi-hereditary cover of the other one. And the combinatorics is given by the normal maximal parabolic Castanusti polynomials. So it's not very interesting. There are only multiplicities 1 or 0. But you can read them off precisely from these diagrams. So everything is very explicit. So now, why do we want to understand this algebra? And our main motivation was we wanted to connect a picture of Kaudis and Chemnitzer using coherent sheaves on a resolution of the Springer fiber with this Hovanov homology picture. We just wanted to give a precise link between these guys, and here is what we know now. So let's look at our nilpotent element n. So let's take the adjoint orbits for this, so nilpotent orbits for this. So then let's take a slice to that. Let's take a Schroeder slice. Like this. And let's take the Springer resolution of that. And tilde. Then we have, inside there, we have the resolution of the slice. And inside there we also have the Springer fiber, and we of course have the components of the Springer fiber, or the pairwise intersections. So what I want to do is, I want to look at a compactification of this resolution of the Slaughter slice. So let's write this down explicitly what this is in a specific case. So if n is 2k, so we have two Jordan blocks of the same size, I can write you down what this set is. The set is can be realized as flags of length k, but not inside ck, inside c2k. So what this becomes is a smooth space. And it should be fixed under the nilpotent, which I denote by n tilde. It's just a nilpotent having two Jordan blocks, but it's now a double size than before. So, and of course, if you fix this space here to be a fixed c to the k, you would get here a Springer fiber. So the Springer fiber is lying inside there. And Vibanov and Milkovich showed that this thing can be equipped with a symplectic structure where these components become Lagrangians. So what we really do is something like intersecting Lagrangians and computing the cohomology. So this is really how I think about this as a sort of Fleur homology. And this is what Seidel-Smith did, and we wanted to connect our construction, which we know now explicitly, with something connected with this geometry. So, and here is the theorem. This again is Ben Webster. So if we look at one of these components of the Springer fiber and the cohomology of it, so we know what it is from this theorem above, then this is the same thing as the X algebra of coherent sheaves on this set. So let me assume that n is 2k to avoid too many notations. So then we take the X algebra inside the category of coherent sheaves on this compactification of the resolution of the slice of the following thing. We would take the structure sheaf on the component and view this as a sheaf on Z. So I take this inclusion I and view my structure sheaf on there. So we explicitly construct a spectral sequence going from here to here, which we show collapses, and we check that it's compatible with the algebra structure. So, and then of course what you would expect, that the same thing holds for pairwise intersections. Like this, but this turns out is not true. There's not even the dimension is correct. And somehow the motivation for me why this is not correct is that this side, how should I say this? This side is somehow symmetric in A and B, whereas this side is not. So it's not invariant under Serre duality, whereas this is invariant under Poincare duality and also under switching of A and P. So what you want to have here is something which is more symmetric, and what you can do is to take omega, the canonical bundle, on this component, and then you can take a square root of it. So this exists because of our statement A upstairs. So there exists a square root of the canonical bundle, and this is somehow fine, it's behaving fine under Serre duality. So this is okay. And you show that this is the right thing to do. And the last statement is one of the motivations why we wanted to consider this, that you namely now can say, okay, what are these sheaves inside here? So they will be all sheaves, so they are not complexes. So I don't have to go to the derived category to describe them, but what they are is they are simple objects of an exotic T structure on coherent sheaves on Z. So the omega half CA are simple objects of an exotic T-structure on coherent sheets of Z. So they won't give you all the simple objects. So it's similar to this extension here. You can describe the other objects, but I don't have a nice description in terms of I checked just half densities of some component. So I have to describe them as more complicated, so I don't want to write them down. But these are parts of the simple objects, and the other ones will be not even sheaves. So they will be really complexes. And we just checked this by looking at Betsov-Kavnikov's setup for exotic T-structures and check these properties layer. So this is as soon as we have this step in here, this is quite easy. But what I think now what we have is a sort of Cauchy duality going between modules over our H star to this exotic T-structure of this coherent sheaves on Z. So projective modules on this side correspond to simple objects in this abelian subcategory. This is somehow the picture. And we know now that this algebra also describes this Floer homology of Seidel and Smith. Also I at least cannot write it down because some of the references which we use I don't understand. So, but if I assume the references are correct, then we can have an isomorphism between our H star and this Floer homology algebra of Seidel and Smith. So that in particular an explicit description of this multiplication. So, and maybe few remarks about the grading. So let's put this here. So on this side, so maybe I should write this at the end. So H star is really isomorphic to this X algebra of these half densities. As algebras, even as graded algebras. So that means the grading on this side corresponds to the normal X grading on that side. So, and again, this grading can be viewed completely explicitly in terms of this diagram. So you would just count the number of clockwise oriented cups in this diagram, so you can really explicitly write down this grading. So, and the last remark is maybe that if we take, if we vary our n of the Springer fiber, where so Springer fiber was embedded into the flag variety FLN. So if we would vary this n and take different copies of the Springer fiber, we can do the same construction, and we get a graded algebra, which is this cyclotomic Hecke algebra of level 2 of type 8. So this level 2 comes from these two blocks of Springer fiber. And then this grading, which we see here, just becomes this grading which was defined by Brandon and Glashchev, and also on the other side by Hovanov and Lauda, via this isomorphism of Brandon and Glashchev, they are the same, on this cyclotomic Hecke algebra. So this is exactly this grading. And if you go to the what I mentioned earlier, you can also realize this as a sub-algebra of a parabolic category O. Then there is the grading exactly coming from the Cauchy grading over there. So that means the graded algebras for the cyclotomic Hecke algebra become graded from this cohomology here or from the Cauchy grading of parabolic category O. So I think I can stop here. Thanks very much.
Thank you very much. Are there questions? Comments?
kind of generators relations do you have with the quasi-hereditary cover of this?
So we write this down in terms of, so at the end you can write it down in terms of these diagrams.
But I'm now indexing by column triptychal instead of.
Yes,
Standard.
okay. So I do this maybe for P1. So you would have this shape, and then you have your standard tableau, which is such a cup, and then you have your, did I say column strip? I think I thought row strip, but it doesn't matter. So I would have this other thing, which I just say, I have to take two straight lines.
Maybe I misunderstood. What does semi-standard mean?
So what I mean is, it is strict in one, I think in the rows now, and it's semi, so it's not, what should I say? Maybe I used the wrong word. So let me say I index it by plus minus sequences of length n. With k minuses, k 0, and n minus k once. I think this is better. So I would put n minus k numbers upstairs, k downstairs, and they have to be decreasing in the rows. So this is what I mean by these tables. So and then you just allow matchings which have less than k cups. So there could be, for instance, the extreme case would be I just have many only orphan points. And this would correspond to a dominant standard model. It has trivial endomorphism.
Two questions. I did not get how you form the square root of the canonical bundles.
So
And this second question is then how you get the T structure.
So this square root of the canonical bundle, I mean, I don't construct, I can construct it explicitly, but only via induction. So if you think about P1, then the canonical bundle is O minus 2, and then the square root would be just O minus 1. But then you have to do this on this P1 iterated P1 bundle such that it fits together. And I can only do this inductively. But the idea is you just take square root for each P1, but in a coherent way. And what was it?
There is a T structure, how you get.
So the T structure is, so you have these half densities, and you just show that they form an abelian, part of an abelian subcategory. They form simple objects in an abelian subcategory, and this will be your T structure. But you first have to extend these guys also by the other ones corresponding to these extra guys, which I cannot write down explicitly. I only can define them inductively. And then you just show by using this Betzukavnikov machinery, so you show that they don't have extensions in the right way.
Other questions? Let's thank the speaker again.